Entropy, or the measure of disorder in the universe. Spontaneity depends on the number of possible configurations that a system can take. This is often regarded as a measure of the overall disorder of the system. And we cannot create energy from nothing. According to the first law of thermodynamics, all matter and energy in the universe are constant. However, we also cannot conserve energy. Energy will always tend to dissipate because no process by which we use energy will be 100% efficient. If I have a battery that I use to do 100 kilojoules of work, recharging the battery will need more than 100 kilojoules to recharge it because there will always be some energy that is lost to dissipation, usually in the form of heat. As well as energy dissipating, matter will also dissipate. The universe charges what we would call a heat tax on all processes. This is where a cut of the useful energy is taken by the universe, just kind of how like Uncle Sam will take money from your paycheck before you get a chance to use it. So we always lose some energy right off the bat before we have any chance to make use of that energy, in what we call this heat tax. Energy is lost both to the heat tax and to inefficiency. The more energy exchanges I have, the more energy I will lose, because each exchange is going to be less than 100% efficient, and they will add up in the total energy that is lost. Any dispersal of energy or matter is described by a state function called entropy, which is abbreviated with a capital S. Entropy is measured on an absolute scale, which means it can never be below zero. We'll always have either zero or positive entropy, never a negative one. The third law of thermodynamics states that entropy of a pure, perfect crystal at 0 Kelvin is 0 entropy, none at all. The higher my temperature, the more my substance is going to vibrate, which means it is going to be less in a pure crystal arrangement. This raises the possible number of configurations and therefore the entropy. So as temperature increases, entropy increases here. As anytime I get above 0 Kelvin, I cannot have 0 entropy. The entropy of a substance at any condition is referred to as its absolute entropy. At standard state, this is called the standard molar entropy. Anything that is greater than 0 Kelvin will be more disordered, and the more higher it is above 0 Kelvin, the more disordered it will be. So entropy value will always be positive. The entropy of an element is not 0 like it is with enthalpy. There will always be some number. You can calculate an entropy change based upon final and initial entropies. So the change in entropy will be equal to the entropy of the system in its final state minus the entropy of the system in its initial state. Standard entropy changes, or delta S naught, or the entropy of the reaction, can be determined by a process just like Hess's law, where the change in the entropy of the reaction is equal to the sum of the coefficients of the products times their entropies minus the sum of the coefficients of the reactants times their entropies. Standard entropy is calculated using the formula where S is K ln of W. K is the Boltzmann constant, which is represented as R over Na. R is the gas constant, Na is Avogadro's number. So we take the gas constant divided by Avogadro's number, and we'll get 1.38 times 10 to the negative 23 joules per mole Kelvin. And in this case, the gas constant we're using is the 8.314 joules per mole Kelvin. W is the number of energetically equivalent possibilities for the system. The change in the standard entropy of a system then will be the Boltzmann constant times the ln of the final count of possibilities minus the Boltzmann constant times the ln of the initial count of possibilities. With natural logs, just like with logs, if I subtract two things, I can divide the one that is being subtracted from the one that is subtracted. So the one that is being subtracted, the initial, from the one that it is subtracting from, the final is divided by the initial. So the change in standard entropy is the Boltzmann constant K times the natural log of the final count of possibilities divided by the initial count of possibilities. This means if we look at our units, because the only units we have are the Boltzmann constant, energetics will be measured for entropy in joules per mole Kelvin. Remember that enthalpy was kilojoules per mole, not temperature related. Mole refers to either moles of a substance or a mole reaction of a reaction in this case. So as an example, using the values of standard molar entropy, can we calculate a change in entropy at 25 degrees Celsius in 1 atmosphere for this reaction, where N2 plus 3H2 goes to 2NH3. The standard molar entropies are 191.5, 131.0, and 193.0. The change in entropy then for the reaction is 2 times the product with NH3 minus the entropy of the N2 plus 3 times the entropy of the H2. This means the entropy change is 2 times 193 minus 191.5 plus 3 times 131. This gives us a net entropy change of negative 198.5 joules per mole Kelvin. This is a loss in entropy, which means the system is becoming more ordered. We can predict the sign of our change in entropy by a number of different processes. Different processes have different effects on entropy. Phase change, moving from solid to liquid to gas, increases entropy. The higher or the more free something is to move, the more its entropy is going to, the higher the change in entropy is going to be. If I melt something, its change in entropy will be positive because it's going to a more free form with more possible configurations. If I freeze something, I'm constraining it to a more rigid form with less possible configurations, so its entropy would be less than 0 or negative in its change. Temperature, the higher the temperature, the higher the kinetic energy according to kinetic molecular theory. This means that energy will be more dispersed. So as temperature increases, entropy also increases. As volumes change for gases, the greater the volume, the more room there is for the gas to spread out. If the gas has more room to spread out, there are a greater number of possibilities and therefore a higher entropy for something with a higher volume. In a mixture, if I combine two things together, there are more possible combinations of configurations than if a single thing is uniform by itself. In addition, energy can be dispersed between both matter and different kinds of matter. So there will be an overall higher entropy for a mixture than for a pure substance. In the same way, combining elements to make compounds will have a higher entropy. So combining a mole of hydrogen gas with a mole of chlorine gas to make 2 moles of hydrogen chloride gas will have a higher overall entropy than those two pure substances by themselves. The number of particles in a system also affects its entropy. The more particles I have, the more possibilities I can have for configurations, and therefore the higher the entropy will be. If I have, for instance, then a diatomic substance like N2 or O2, going from N2 as a gas to 2N atoms will cause a slight increase in entropy. This is amplified or increased if the diatomic standard state is a solid or a liquid rather than a gas, because it first has to vaporize, increasing entropy, and then split apart, increasing entropy further. The higher the number of moles I have in my system, the higher the possible configurations, because there are more things, and therefore the higher the entropy. So, for instance, 2H2 as a gas plus O2 as a gas going to 2H2O as a gas goes from 3 moles to 2 moles. Fewer moles means that I'm going to decrease my entropy, because there are fewer number of moles, therefore fewer possible configurations. If I have anything with a similar size and shape in its molecule, it generally has a higher entropy if the molar mass is higher. So if I look from HF to HCl to HBr, as I'm going up those from left to right, they're increasing in molar mass. So entropy tends to increase with those. If I am of a similar weight and a similar shape, then a higher charge will tend to reduce entropy. For instance, calcium sulfide has a lower entropy than potassium chloride, because those higher charges tend to cause things to stick together more. They can't spread out as well.